So now we can switch to another topic, which is routing. And here we can look at an exercise. It is quite simple, but I think significant. So we have this network that is represented in the figure. You see all the addresses that are assigned to each subnet, to each IP net, and there is a number of There are a number of routers and hosts connected to the networks, plus point-to-point links between the routers. So we have to draw the graph of the network and calculate the shortest path, considering only nodes and arcs, and not considering the networks attached. And then we have to calculate the shortest path between router R1 and all the other nodes, so all the other routers, using Dijkstra. And in the first case, we consider the same cost for all the arcs. Then there is another repetition of the same question, but considering a cost which is inversely proportional to the capacity of the links. Here you can find the links, the capacity of the links on the picture. Then we can, the last question is regarding the RIP protocol. The RIP protocol is using distance vector, and we have to indicate concisely the information that is included by each node in the distance vector that it sends to the neighbors. So we can start drawing the graph of this network, and so I don't replicate the picture, but I go directly to the graph, which is the following. So here we have R5, then we have R1, then R2, R3, R6, and R7, R4, and that's all. Okay. These are the links. All the links have the same cost, so we can assume that the cost is equal to 1. And we have to apply Dijkstra considering R1 as the root. Can be either the source or the destination. Is the same because all the links are symmetrical. So I will use the shorthand form of the Dijkstra algorithm using the labels that are written on each node. So we start with the initial step where I can write the distance. The first element that I write in the parentheses is the next hop or previous hop on the shortest path. The second element is the distance calculated compared to R1. Okay. So initially R1 is set to 0, of course it will remain the same, and we can start setting the neighbors at the distance 1, since links are, we have direct links. All the other nodes are set to distance infinity. Because they don't have the direct links with R1. Okay. And initially, the shortest path set contains just R1. So R1 is immediately with a permanent label, and it will not be considered anymore. Now we have to find the arc that is connected to the shortest path, that is in this case is just R1, which has the shortest distance at that specific moment. Here we can choose between R2 and R5, and let's say that we select previously we select, just want to replicate the same solution. So we select R2. Okay. So R2 becomes permanent, and it becomes a part of the shortest path. And now we have to update all the nodes that have a direct connection with the shortest path by considering their connection to the elements of the shortest path and updating the value if they have the value is less than what is currently the distance value. And so, for example, in the case of R5, we can write, actually it has direct connection with R1, so we don't modify anything. R3 has a direct connection with both R1 and R2. Sorry, R2 and R5. So I can write here R5, 2, for example. R6 is a direct connection with R2. And then the other ones have no direct connection with nodes that are inside the shortest path. So here we remain at infinite distance. Okay. Now we have to select the neighbor of the shortest path which has a shorter distance. In this case is for sure R5. This becomes permanent, the label becomes permanent, so we can include it in the shortest path as well. And update the other nodes as a consequence. So R7 has a connection with R5. R5 has a distance 1. R3 has a connection with both R2 and R5. Let's say that we can also change here, because we can choose randomly one of the two. Then we have R6, which is again connected to R2, doesn't change. And also R1 doesn't change because it has, sorry, R4 doesn't change because it has no direct connection with the shortest path tree. Okay. Now again we have to choose another label to become permanent, and here we can randomly choose between R7 and R3. Let's say that we choose R7. So R7 becomes a part of the shortest path tree, and again we have to update all the distances. So here this remains the same. This remains the same as well, and this becomes R7. R7 has a distance 2, so it will be R7 distance 3. Okay. We have to include another node. We can choose between R3 and R6. Let's say that we choose R3. Also, this node becomes part of the shortest path. We have to do updatings, so this does not change. And R2 here, R3, sorry, is at the distance of 2, so also the R4 doesn't change. Here we include R6, and R4 again, it can be updated, but it does not change, so we can include finally R4 at the same distance, distance 3, and connected to R7. Okay? So the shortest path 3 is this one. Remind that it is referred to R1. Okay? So if you take another node as the root of the shortest path 3, you will have another shortest path 3. The second part of the question asks to to specify distance vectors that are sent from each router to the neighbors. And so here it's better if I copy this picture. Let's see if I can. Otherwise I have to draw everything again, which is quite lengthy. And we can, for instance, take one node. It should be done for each node, but we have time just to show one example. So let's say that we take the node R3. Okay. So first of all, we have to write the routing table of R3, and to write the routing table of R3, we have to take all the networks, the destinations that are visible from this node, and always reminding that we are writing the routing table and not the interfaces. So interfaces should not appear, okay, because they are not part of the routing table. For instance, from router 3, we see this network here. Let's call it A. Then we see the network B, which is this one. We see network F, is this one. We see network D, and we see network E, and we also see network C. Okay. These are the three networks. The one that is 16/30 and 21/24 and 15/24, they are connected to the interface of the router, so they don't appear in the routing table. So in the routing table, now I write each entry in terms of network prefix using the letters, because otherwise it takes too much. So this is A, B, C, D, E, and F. Here you should write instead the network prefix with also the net mask. So you should write, for instance, instead of A, you should write 131.175.16.0/30. Always remember the length, or the in terms of slash or in terms of net mask. Then there is another column. This is the prefix this is the distance, and then this is the next hop. So in the column of the distance, we have to write the distance. And remember that you should not use the tree that we have just computed, because that is the shortest path tree referred to R1. Instead, here we are looking at R3. This is a very simple case, so you can easily figure out the distance just by looking at the network. For instance, A is at the distance 1, because it takes, you go through network, this network here above, to arrive to A. It's just one hop away. B is at the distance 1 as well. And D is at the distance 1. And so F is also at the distance 1. C is at the distance 1 as well. The only one that is at distance 2 is network E. Okay? And then here you should write the next hop. So for instance, for network A, the next hop is the interface of this router here, R2, which is 131.175.15.254. Okay? And so on for all the other interfaces. So what is the distance vector that is sent from router R3? You have just to take the first two columns of the routing table. So it's a set of destinations and a set of distances. Here there is no indication that split horizon or split horizon with Poisson reverse is used. So the distance vector that R3 sends to all his neighbors is always exactly the same. Okay? It doesn't change from neighbor to neighbor, and it will be sent to R2, R5, R4, and I think that's all. There are no other, no, actually there is also R6, because R6 is connected to the same network that is connecting the interface of R3, so it's a direct neighbor. Okay, this is not really very difficult. In case you have instead set split horizon, then you must distinguish between destinations that are reached by certain next hops, and each time the router sends a distance vector to the neighbor that is next hop for those destinations, either it does not notify those destinations or it does notify them at an infinite distance in case of a split horizon. Clear? So let's switch to multiplexing. In multiplexing, exercises are more or less all the same. We can take a simple one, that is this number 9. So in this case we have a TDMA mobile radio system with 100 voice channels per carrier. Each voice channel has a rate of 32 kilobits per second, and we assume cells of 300 meters. This means that the radius is equal to 300 meters. Okay. The efficiency should be not smaller than 90%. we have to calculate guard time, frame length, burst length in bit, carrier rate, and we can assume a propagation speed of 3 by 8 to the 9 meters per second, which is equal to the speed of light in the empty space. So, first of all, we can calculate the guard time, Tg. If you remember from the lesson, the guard time should be set to the maximum propagation delay in the network. So here we have a cell where we will have a central antenna here, that is the so-called base station, and all the sources and destinations are distributed in a circular area, and the maximum radius is R, so the radius. Okay. So if you have a source and a destination, the worst case is when they are on a diameter, in the opposite extremes of a diameter. Okay. You can call it this propagation delay tau, and in order to have a good say resilience to movements of the stations, so to avoid that we have collisions in some places of the network, we have to do the guard time larger or equal than the maximum propagation delay. Actually, here in the solutions, this is called 2 tau, so let's call it 2 tau. So that Tj should be equal to 2 times tau. And the tau is actually given by the distance, in this case is the radius in meter, divided by the speed of light, which is already given in meter over seconds. And if you do the computations, this is 1 microsecond. Okay. So it means that the guard time should be 2 microseconds. So when we are building the frame, the TDM frame, we start from a certain point and certain time, this is time, and we will have an interval that is the frame duration, TF. This frame will be composed by bursts separated by guard times. Okay, so the stations transmits data in the bursts, and then they stop transmitting. Then all the stations wait for a guard time, which we have already computed is this Tg, and then another station will start transmitting. We can call the duration of the burst T. Okay. Now, if you take the interval that is composed by T and Tg, this is the time that is dedicated to a station. But in this time, the system is occupied, the channel is occupied only for T seconds, and instead everything is idle for Tg seconds. So the efficiency that is mentioned here in the text, you can call it eta, that is 90%, so it is 0.9, can be written as the ratio between the time t and the time t plus Tg, because the system is occupied only for t seconds over t plus tg seconds. Okay. So if we develop this equation, this is actually the minimum efficiency. We can easily find t, okay, because now we can write that 0.9 t plus 0.9 tg is equal to t. So 0.1 t will be equal to 0.9 tg. So t will be actually 9 times tg. Okay. And since we have already computed tg, we have immediately that t will be 18 microseconds. Okay. Now, what is the total frame duration? Here the text says that there are 100 voice channels, so the total frame duration is very simple. It will be 100 times t plus tg. Okay. Which is equal to 100 times 20 microseconds, which is 2 milliseconds. Okay. In the basic dimensioning of TDM systems says that each tributary should produce the number of bits that are transmitted in each time slot in a time that is equal to the duration of the frame. Okay. And we know that each tributary is producing at a rate that is, let's call it V, which is this one. Okay. V is equal to 32 kilobit per second. Okay. So how many bits each tributary is producing in the duration of a frame? The number of bits B is simply given by V multiplied by TF, that is 32 kilobit per second by 2 milliseconds. In the end is millisecond and kilobit cancels out, so you have 64 bits. Okay. This is the quantity of bits that is produced by each tributary, that is produced by a tributary during the duration of a frame at the speed of V, but must be transmitted out of the multiplexer in the duration of one time slot. So from this, knowing this, you can calculate what is the output speed of the transmitter, of the multiplexer, just by dividing the total number of bits, B, for each tributary, to the duration of the time slot. Okay? And here we are not counting the guard band, because the guard time is empty, just the T. And this is 64 divided by T was 18 microseconds. This means megabit per second. which is 3.55 megabit per second. Okay? All the exercises on multiplexing are very similar to this. Sometimes instead of having guard bands, you have extra bits that are for control bits. You have to take into account about additional control bits that becomes the header of the system. Finally, we can go to the local area networks, and we can solve this simple exercise. Here we have a switched LAN made of 3 switches and 4 stations. Each station has a MAC address, and the switches are S1, S2, and S3, with the port numbers that are represented in the figure. Port numbers are important because when we have to compete to fill up the forwarding tables, we need the port numbers. And the forwarding tables are initially empty, and we have to write down the evolution of the forwarding tables when a sequence of 4 frames is exchanged between A and C. And the frames are given in terms of source and destination. So we have A to C, C to A, A to C, and C to A again. We have to indicate the forwarding behavior of the switches for each frame and the content of the forwarding tables after each packet processing. Moreover, we have to say which frames are received also by B and D, which are not the source and the destination, but they receive frames in case these frames are forwarded using broadcast, okay, the broadcast mode. So we can start writing down the 3 tables. Here we have S1, S2, S3, as you know, the tables are composed by 2 columns. The first column contains MAC addresses, and the second column contains the ports. In these exercises, you have to follow the path of each frame from the source to the destination, and to understand each time if the switch is behaving in a unicast or a broadcast mode, and each time the switch receives a frame, you have to remember that you have to perform the learning process and then the forwarding process. So let's start from the first frame, which is A to C. So the frame is produced by the station A. It arrives to switch S1 on the interface 1. So S1 performs the learning process. In the learning process, it will look at the source MAC address of the frame, which is A in this case, okay, and write down in the new entry of the table the MAC address associated with the input port, which is in this case 1. S1 behaves, now there is the forwarding part, so S1 behaves in the broadcast mode because there is no entry for the destination, which is C. Okay. C is already unknown. So this frame is forwarded on port 2 and also on port 1. And specifically on port 2, it will arrive to the destination B. So we can write here, take the node that AC has arrived here. Okay. Then on the other port, it goes to switch number 3, so S3. S3 performs again the learning process, and so the entry is again A associated to port number 1. and it forwards the packet on port number 2, which is the only remaining port, and it will go to switch number 2. Switch number 2 gets the packet from port 3, so it performs learning, A3. C is unknown, so the frame will be forwarded in a broadcast mode. It will arrive to D and also to C, which is the destination. Second frame sent from C to A, so first it gets into route number 2, S2, so switch number 2. Learning part, now C is the source and A is the destination. The packet arrived from port 1. Since now the destination is known, switch S2 will behave in a unicast mode, so the frame will be sent directly to S3. S3 again performs the learning part, 2, it's port 2, and it will forward the packet on port 1. Port 1 will arrive to S1. S1 knows the destination and learns about the source. Okay. So again, the packet will be forwarded in a unicast mode. Now there is another packet from A to C, and then another packet from C to A, and you can immediately notice that in both cases packets are always forwarded in a unicast mode. So basically now the routing tables with A and C are completely have been completely filled in, and so each new packet that will be sent from A to C or to C from A will be always managed in a unicast way. So in the end, the only frame that is received by B and D is frame number 1, and B and D both discard this frame because they check their MAC address, their own MAC address, with the destination MAC address, and the frame due to MAC address are not matching. In many exercises, you find that at a certain point, after this phase of sending frames that allows to fill up the forwarding tables, the exercise continues by disconnecting one of the stations from one side and reconnecting it on the other side. Let's say that you here disconnect C from here and you reconnect it to S1. So what happens in the case that after this change in the topology, A sends a packet to C, okay, a frame to C. Since S1 is not aware that C moved, and also S2 is not aware, the packet will be lost because S1 will send it in the unicast way, unicast mode through port 3, and then from there it will not reach the destination. If instead C sends a frame somewhere to any destination, then S1 is aware that C changed its position. Maybe S2 is not aware, so for instance, if C sends a frame to B, then S1 is able to learn that C moved, the frame will arrive to B. But if A sends then later a frame, D sends a frame to C, the frame will be lost because S2 is not aware that C is moved. Okay. So you have always to take care about the path of the frames, and in case of changes of the position of the stations, there is the possibility that frames are misrouted and so that they get lost. Then, okay, two very quick exercises on multiple access to shared medium. For instance, we have this first exercise about Aloha protocol. Okay. So here we have a network based on Aloha, multiple access. The packet duration is T. We assume that the traffic on the channel, the average number of transmissions in the duration of the frame T, is 1.649, which is equal to the square root of E, times the number of successfully transmitted frames. Probably during the class I didn't mention the fact that when you are talking about G and S, since everything is referred to T, they represent the average number of packets that are respectively transmitted and transmitted successfully in an observation window which is equal to T. Okay. Of course, if you look the system for more than one T and the system is stable, the ratio between the observation window and the number of packets that you have will also be equal to G and S. But you can always think about G and S as the number of frames transmitted in a time T or successfully transmitted in a time T. So since here we have Aloha, unslotted Aloha, so simple Aloha, you know that the basic relation between S and G is that S is equal to E to G times E at the power of minus 2G. And it is not specifically mentioned, explicitly mentioned here, but we have also to assume that the number of stations is equal to infinity. Okay, otherwise this equation doesn't hold. So now we can also, from this equation, we can write that G over S is equal to E to 2 times G. Okay. And here we have that the problem specify that the traffic on the channel G is equal to square root of E times S, okay, which is the number of successfully transmitted frames. So G divided by S is equal to the square root of E. Now you can take these two equations and combine them. You have that E to the 2G is equal to the square root of E, which is also equal to E 1/2. Therefore, from this relation you can calculate G. Okay? G is equal to 1/4. Now, if you replace G in the equation, you can also calculate the throughput, which is 1/4 by times E minus 1/2, which results in 0.125. Okay. Disappearing. Problems that you will find are very simple, like this one. Sometimes during the exams they can also appear as theoretical questions at the end of the text. Final exercise about SMA CD. The transmission rate on a channel is R and the minimum packet length is L. The propagation speed is equal to 2/3 of the speed of light, so this means that we are considering transmission on a guided propagation medium, and we can also call this, just not to avoid confusion, the delay per unit of length. Okay. Is equal to 5 microseconds per kilometer. We assume that the ratio between the ratio A between tau, in this case is not tau per unit of length, but is the delay, and the transmission time must be equal or smaller than 1 for system efficiency, and we have to calculate the maximum distance. Actually, in this problem, we consider that this ratio must be equal or smaller than 1. Okay, so we can write that A, which is tau divided by T, equal or smaller than 1. But we know that this condition has a stronger actually condition if we want to make collision detection working, and that is that A, which is tau divided by 2, is sorry, the condition, let's start with that, with this. The condition is that T must be at least larger or must be at least equal to 2 times the delay. So it must be larger or equal than 2 times the delay. Okay. So this means that this translates into the relation that tau divided by T, which is A, should be less or equal than 1/2. Okay. So the condition that is actually mentioned in this problem is for system efficiency, but the condition that is due to the correct function of the collision detection, so the working condition of the collision detection is stronger. So the condition set by the problem will be always met provided that collision detection is working. Okay. But in any case, we can refer to the first condition that is given in the problem, because then the calculations are exactly the same. So the question is to find the maximum distance between the stations that comply to that condition. And we know that the transmission occurs at the bit rate R, and the length of the station is 1000 bits in all the cases except the last one, that is 1000 bytes. So we can immediately calculate the duration of the transmission frame, which is equal to the length of the frame divided by R. And then we know that the distance d that we have to find is equal to, so we have that tau is equal to d by tau per unit length. So in the first case we have that t, we have 10 megabit per second, and L is equal to 1000 bits. So t will be 100 microseconds. Okay. So since if we are compliant to the condition of the problem, tau must be equal to t actually on the extreme. It means that the maximum distance by tau per unit length must be equal to t. So the maximum distance will be equal to t divided by tau per unit length. Okay. So if t is 100 microseconds, the distance is 20 kilometers. So 100 divided by 5 in kilometers. Then in the second case, we are transmitting 10 times faster, so the transmission duration is 10 times less. D will be equal to 2 kilometers. Third case, we are transmitting again 10 times faster. So we have a transmission duration of 1 microsecond. Distance will be 200 meters. Third case, we are transmitting actually, so we have longer frames. So the transmission time, we are transmitting at the same speed, 1 gigabit per second. The transmission time will be 8 microseconds. So the distance will be 1.6 kilometers. Okay. Actually, if we want to enforce instead this other constraint, which is the one that allows the collision detection to work, on this case the maximum distance will be t divided by 2 times tau pool. Let's call it t prime. So you have just to divide everything by 2. Okay. Here you have 10 kilometers. Here you have 1 kilometer, 100 meters, and 800 meters. Okay. This technique of setting the length of the frame exactly in the same number, but instead of bits, of bytes, so you are increasing the length of the frame, is what is actually adopted in Ethernet standard. When we are going from 100 megabit per second, so from fast Ethernet to gigabit Ethernet, and we want still to use broadcast medium, like for example a hub. And these are called jumbo frames. So all the fields of the header are then enlarged and multiplied by 8. So in this case you are increasing the length, so you can use the network instead of with a limitation of 100 meters, which is very severe, at least over 800 meters. Okay, that's all.